Hello, everyone. I welcome you to this IEEE Milestone dedication event. I'm happy to say that we have attendees from all over the world joining us, including Pakistan, Indonesia, Canada, India, Australia, and Panama, from countries all over Europe and all across the United States, and from many other parts of the world. This is great, so let me give you a big, wide welcome. Now, some of you might be wondering, what in the world is IEEE? And what in the world is an IEEE milestone? You may have had a chance to answer these questions by exploring our website at gwamilestone.com, or you may already be a longtime IEEE member such as myself. Our IEEE President-elect will be talking about some of these points following my opening remarks, but very briefly, let me say that IEEE is a worldwide organization with about 420,000 members who are engineers and scientists, and we help make the world go round. IEEE milestones honor the most important of these endeavors, and they teach us the story of how these major accomplishments came to be. Indeed, our program today will discuss the astonishing prediction about the nature of gravity made by Albert Einstein while a professor at the University of Berlin in 1916, and which was proven for the first time 99 years later. In case it doesn't already show, I love history. I've learned a lot of the stories behind many of the astounding accomplishments while working on over a dozen IEEE milestones over the last 10 years. And I've been lucky to be able to learn from some of the brightest people on Earth. I need to give a big thank you to the team members with whom I've been working on this dedication event. This includes Will Robinson, who is IEEE-USA Vice President of Government Relations, and with whom I rendezvoused in Glasgow, Scotland back in 2019 in order to get this milestone approved by the IEEE History Committee. As you can imagine, a learned team from around the world must first judge a milestone to be historically significant and must also ensure that the citation as cast on a beautiful bronze plaque is factually correct. Today we're going to hear about the historical significance of how three massive antennas in both the US and Italy were able to confirm that prediction of Einstein's. As part of my love of history, I've been reading a book entitled Endless Frontier, which chronicles the critical role of scientists and engineers working at research centers and universities such as MIT and Caltech during World War II. Their success forged an alliance of the government with schools and research centers across the country, and this led to the creation of the National Science Foundation in 1950. The resulting government funding of scientific research has led to advances in computing and communications, including the ability for all of us to come together in cyberspace for today's gathering. As you will see from our series of speakers, such alliances have borne amazing fruit, not only in America, but also in Europe, Asia, and elsewhere in the world. So not only do we have attendees from around the world with us today, but our speakers are an important international group of scientists, as well as dignitaries from organizations that provide essential funding for scientific research, leading to benefits for our populations and a better understanding of our universe. While it's unfortunate that we can't be together in person for today's event, our audience today is much larger than the number who would have attended the three separate events that were originally scheduled for last summer. Instead, here we are, all together from around the world at a single event. I must thank a few more people for their work in making today happen. Our core team consisted of Will Robinson, who met with me in Scotland, and who wrote the successful milestone proposal with critical help from Rich Abbott of Caltech and LIGO. Matt Francis has been our IEEE Region 5 coordinator for the sections near the Livingston LIGO site. We've also had tremendous help from Bernardo Tellini, who is a professor at the University of Pisa and who has served as our primary European IEEE contact. Bernardo enlisted the help of Stavros Katsanevas, who is a professor at the University of Paris, a director of the European Gravitational Observatory, which hosts the Virgo antenna in Italy, a past director of the Laboratory of Astroparticle Physics and Cosmology in Paris, and also a deputy director of the National Institute of Nuclear and Particle Physics of the French funding agency CNRS. I need to give a big shout out to the team at IEEE-USA that allowed today's event to be transformed from a slate of international participants to the reality of this online event. This includes our videography and rendering team of Jonathan Cho and Corey Ruth. In addition, we thank Aline McNall for being our liaison with the National Science Foundation, and Kate Duncan, who is the 2021 IEEE-USA President. I also want to thank the IEEE Foundation and its Executive Director, Karen Gallucci, for its funding of the activities of the IEEE History Center and its Milestone program. Thank you also to the IEEE section officers in Baton Rouge and New Orleans, Louisiana, and Richland, Washington, for soliciting proclamations and video recordings from Richland Mayor Ryan Luxon and Livingston Mayor David McCreary. Thanks also to Dr. Sherry Wen for her work with the Washington Governor Jay Inslee, and to Will Robinson for his work with the Governor and Lieutenant Governor of Louisiana. You will hear some of these dignitaries during our program and also find proclamations and videos from them posted on our website. Finally, thanks to the IEEE Consultants Network of Silicon Valley, of which I am a director, and to Sherry Wen of the UNESCO Washington State Center for their funding of mementos, which honor the milestone and the 3 observatories. Our first speaker is IEEE President, Dr. Ray Liu. At the University of Maryland, College Park, Dr. Liu is a distinguished university professor and the Christine Kim Eminent Professor of Information Technology. Dr. Liu is a fellow of the American Association for the Advancement of Science and of the U.S. National Academy of Inventors. He is also an IEEE Fellow for contributions to algorithms, architectures, and implementations for signal processing.
Thank you, Brian, for that introduction and for your kind invitations to participate today. Hello, everyone. Thank you all for joining us today for this very special IEEE milestone dedication ceremony for 3 gravitational wave antennas. As 2021 President-elect, it is my pleasure to take part in these celebrations. This event is in recognition of the detection of gravitational wave as predicted by Albert Einstein's 1916 theory of general relativity, as well as the fundamental achievement of the direct measurement of gravitational wave. I would like to thank everyone for taking the time to participate in this international ceremony. It is quite a feat to simultaneously dedicate Plaques at 3 unique locations around the world. By celebrating the pride and prestige of our professions, we demonstrate how engineers, scientists, and technologists contribute to our global community and have helped to build today's technologically advanced world. For those who are unfamiliar with IEEE, we are the world's largest technical professional organizations. IEEE's core purpose is to foster technological innovations and excellence for the benefit of humanity. IEEE is a world-leading publisher of trusted, high-quality technical information, a principal organizer of international conferences, a value provider of educational material, and a developer of widely used international standards. Our nearly 420,000 members across 160 countries are vibrant, diverse engineering and technological professionals who are committed to elevating their professional image, expanding their global network, connecting with peers locally, and giving back to their community. Dedicating an IEEE milestone take tremendous effort, and the members across the numerous IEEE regions are to be commended for their generous gift of time in bringing this dedication to completion. As the detection of gravitational wave had become a global effort, so was the planning and organizing of this international ceremony. In particular, I would like to thank my IEEE colleague, Baton Rouge Section Chair Don Covillian, New Orleans Section Chair Chen Wong, Richland Section Chair Leo Fitzfield, and Italy Section Chair Bernardo Terlini. I would also like to thank the core program planning team led by Brian Berg, who is the Region 6 History Chair and Milestone Coordinator, a member of IEEE History Committee, and a Director of the IEEE Consultant Network of Silicon Valley. Some of you may be asking, what is an IEEE milestone? The Milestone program honors significant technical achievements in electrical, electronic, and computer engineering and the associated science. Funded by donation to IEEE foundations and administered by our History Center, the program recognizes great moments throughout our world's long history of technical innovations. The program began in 1983 as part of IEEE's centennial celebrations. Today's milestone is our 213th worldwide. It is the first milestone for both Baton Rouge and Richland section and the 7th for the Italy sections. It is also the first milestone to be dedicated in 3 IEEE regions. For Region 5, this is the 13th milestone, the 29th for Region 6, and the 51st for Region 8. IEEE milestone help to increase the public's understanding of the contribution of society made by electrical, electronic, and computer engineers, and the stride made by countless technologies as they sought to advance technology to benefit humanity. They are symbols around the world of how electrical, engineering, and computing have helped to build the modern world and bring people closer together. It is my privilege to recognize these pioneering events and the people behind them. They serve as landmarks in the progress of technology and in the progress of civilizations. I am honored to be a part of these celebrations. I would like to thank you all again for joining us today, and I applaud all the organizers of this extraordinary, inspirational program. Thank you.
We're pleased to have with us today the Honorable Sethuraman Panchanathan. He is a computer scientist and engineer and is the 15th director of the U.S. National Science Foundation. Dr. Panchanathan is also a fellow of the IEEE, an honor he received for his contributions in compressed domain processing and indexing, in visual computing, and communications. The NSF first started funding LIGO feasibility studies in the 1970s. LIGO is one of the most ambitious projects ever undertaken by the NSF. The NSF's appreciation of the need for a far-sighted perspective when it comes to complex scientific research and engineering is on display in today's event. As such, today we salute the absolutely essential role that NSF funding has played over the last 70 years. Dr. Panchanathan will now share his thoughts about the extraordinary achievements that are a direct result of the NSF's perseverance in this program.
Good day to all of you. I am Sethuraman Panchanathan, and I'm so honored to join you today on behalf of the National Science Foundation in recognizing the amazing accomplishments and discoveries of the LIGO and Virgo collaborations. A century after Albert Einstein first predicted the existence of gravitational waves, they were detected emanating from the collision and merger of two black holes in a cosmic event that occurred approximately 1.3 billion years earlier. This amazing feat was made possible by sustained investment, dedication, world-class research, and strong collaborations across our country and around the globe. It took decades for the vision of the early pioneers, in gravitational wave science to become reality. It also required sustained support from governments and academia. From the first awards in the 1970s to the construction of the antennas in Livingston, Louisiana, and Hanford, Washington, where these milestone plaques will commemorate this achievement, the National Science Foundation invested more than $1 billion over 4 decades. In fact, LIGO was the first of our agency's major research equipment projects and highlighted NSF's unique role and ability to fund the high-risk, high-reward research infrastructure that propels science forward and transform our future. But maybe most importantly, it was the product of the curiosity and ingenuity of those initial visionaries and 1,000+ scientists and engineers across more than a dozen countries who worked as a team to tackle a grand challenge. LIGO's success was possible because of superb engineering in many of the areas of importance to the IEEE, such as photonics, low noise electronics, digital signal processing, and servo control systems. Among the prestigious awards associated with LIGO is the 2017 Nobel Prize in Physics, awarded to Ray Weiss, Kip Thorne, and Barry Barish. It is an honor to be able to thank them today, once again, for their contributions to science and human knowledge. The discoveries did not end with that initial detection of gravitational waves on September 14, 2015. In fact, the LIGO and Virgo collaborations have gone on to be prolific in producing groundbreaking results and changing the way we view the universe. We have opened a new window through which to observe, and it has allowed us to see what could not be seen before. For instance, there have been numerous detections of black hole mergers, including black holes with masses that are difficult to explain. We have also observed the merger of 2 neutron stars, answering questions about the origin of the heavy elements in the universe. I am so excited for what the future holds. NSF has continued to invest in the future of LIGO and the facility's ability to study gravitational waves and their origins. Equally important is the investment in the generation of scientists and engineers that have been inspired by your work and that will one day build upon it. That is why strong education and outreach efforts around these accomplishments and the science that underpins them is so critical. The strong partnerships between the LIGO facilities, academic institutions, and the states of Louisiana and Washington are central to this endeavor. I am so pleased to see the broad partnerships that have formed between academia, government, and other organizations to expand the educational impact of LIGO. For example, the partnership with Southern University is an excellent example of how we can broaden the reach and impacts of these world-class facilities. I am also thankful for the commitment the state of Washington has made to support educational initiatives at Hanford site, building a new education center there. Throughout history, we have sought to understand the great mysteries of the universe. Nothing has captured our collective imaginations and study more than the beauty and wonder of the cosmos. Perhaps this is because, as Carl Sagan said, we are made up of star stuff. And that is a truth the LIGO and Virgo collaborations have helped make even clearer. Your efforts have unlocked another mystery of the universe and raised new questions for us to answer. Thank you again for allowing me to join you today, and to IEEE for this most deserved recognition of this historic achievement.
Till recently, the 2 founding members of IGO hosting the Virgo detector were the CNRS and the INFN. Recently, we have a new member, and this is the Dutch colleagues from NICEF. So the first founding member that I have the pleasure to introduce is the CNRS, and essentially Antoine Petit. Its President and Director General since 2018. He's a professor of exceptional class, and he has a PhD in computer science from the University Paris Diderot, where he specialized in formal methods, mostly based on transition systems.
It's an honor and a real pleasure for me to speak on behalf of CNRS for this IEEE Milestone event, which honors a truly exceptional achievement, the detection of gravitational waves. This prestigious international recognition honors significant scientific and technical achievements of the LIGO and Virgo collaborations. Not only did LIGO and Virgo detect gravitational waves, but this scientific achievement is no less than the confirmation of Albert Einstein's 1916 theory of general relativity more than 100 years ago. The signal itself was emitted more than 100 million years ago, and LIGO and Virgo are now able to routinely detect even more distant ones. This is truly impressive science. But the technical achievements are no less impressive. For more than 2 decades, passionate researchers have been working to build and run certainly the most delicate instrument on Earth, gravitational waves antennas. These unbelievable instruments are able to detect variations the size of an atom and smaller to a distance as large as the distance to the Sun. This is truly impressive and, for a non-expert like me, beyond my imagination. What is also impressive is the time and patience it took to achieve this. Decades of hard work to build, adjust, and improve the instruments, and then improve them again, during which funding agencies and research organizations had to be convinced to fund these expensive experiments. I think it's worth mentioning here that this discovery would have never been possible without the long-term commitment of these research organizations and of the governments who fund them. We are indeed very fortunate that this could be achieved in our lifetime. CNRS joined this effort in 1993 when, following a now famous Fleury report from the name of the particle physicist chairing the committee, recommended that France invest in the detection of gravitational waves using the technique of gravitational waves interferometers. Soon after, the Virgo project was approved by CNRS and INFN. Construction began in 1997 in Pisa, the very site the IEEE milestone plate would be installed. 20 years later, in 2017, Virgo and the 2 LIGO antennas jointly detected gravitational waves from the merging of neutron stars, and the same year, the Nobel Prize in Physics would be awarded for the discovery of gravitational waves made just 2 years earlier. To finish, let me back up a minute. I am told that gravitational waves come from the collisions of binary neutron stars or of black holes that occurred anywhere from hundreds of millions to nearly 3 billion years ago. We are also told that these events travel through the universe virtually unimpeded and procedure-minute changes as small as 1,000th of a proton diameter in the arm length of these antennas. I can't help but note how extremely amazing all this is. The numbers we hear are either immensely large and immensely small. The events that create these space-time waves are cataclysmic. The objects involved, neutron stars, black holes, are extreme. The energy released tremendous. The space-time distortion that is detected is small. That's why this discovery is so important. It tells us of our galaxy and beyond. Furthermore, it tells us how our universe was millions or billions of years ago. It's also a way to probe inside the stars themselves, and it is a new window into our universe. Thank you, and congratulations again to the teams that have achieved such an impressive discovery.
The second founding member of IGO, supporting Virgo, is INFN. And I have the pleasure to introduce Antonio Zoccoli, who is the president of INFN since 2019. He made his studies in Bologna, where he became professor in 2003. He was also the director of the INFN section of Bologna, president of the Fondazione Giuseppe Occhialini, and very early became member of the INFN executive board, where he was responsible for high energy particle physics and also scientific computing and large research infrastructures. He was also for some time vice president of INFN. He is also an unfailing supporter of the Virgo and IGO program, and I have the enormous pleasure to present him to you.
Once upon a time, this is the starting point of every beautiful tale, and is a good incipit also for our story. Once upon a time, in the year 1916, Albert Einstein postulated for the first time the existence of gravitational wave. 100 years later, in 2016, the first detection of gravitational waves was announced. 1916-2016, a period of time that must make us think. What is the meaning of the 100 years that have passed since the concept of gravitational wave was introduced by Albert Einstein, until its existence was experimentally proved by our interferometers? It took a century-long journey to realize the discovery that opened a new era in the exploration of our universe, the era of gravitational and multi-messenger astronomy. Well, these 100 years represent above all the importance, when doing science, of having vision, courage, and determination. Vision, because we must be able to imagine and look very far beyond the horizon of our life and of our scientific and technological knowledge to design the future of research. Only in this way we will be able to design and plan the path and the tools necessary to make it possible. Courage, because a scientific undertaking of this importance means accepting an extremely demanding challenge without having a priori certainty of how it will end. Investing in it, therefore, means taking on great responsibility and determination, because it is our most precious ally to face obstacles of a long, bumpy, and not at all obvious path. With vision, determination, and courage, we were able to demonstrate the existence of gravitational waves. After a century of their theoretical prediction, we were able to measure what Einstein believed would never be possible to measure. It took a century, yes, because to do this, we had to design and develop cutting-edge technologies, ad hoc technologies that did not exist before. We had to produce innovation. The history of science told us the progress is tightly linked to the progress of technology. To reach this goal, we developed a sophisticated system of super attenuator of seismic noises, ultra-high vacuum, very high precision lasers, extremely smooth mirrors, accurate algorithm, and powerful computing system for data analysis. Technologies pushed beyond the imaginable to achieve the finest measure ever. We have designed and developed a cutting-edge solution in all this sector to build our interferometers, frontier technology that is already finding application in our society. A technology, therefore, which does not only the good of the science, but also the well-being of people. LIGO and Virgo interferometers are our pride. And it is with this pride that today we receive the important recognition that the Institute of Electrical and Electronics Engineers has decided to dedicate to the instruments that have made possible one of the most exciting and successful scientific enterprises ever. We therefore thanks IEEE for this recognition. And thanks EGO, the European Gravitational-Wave Observatory, and thanks to all those who have had the vision, the courage, and the determination to pursue a dream that has lasted 100 years, leading to success. And I want to address a special thank as president of the National Institute for Nuclear Physics to one of our best scientists, Adalberto Giazzotto, a visionary, courageous, and tenacious person who has inspired and accompanied the work of gravitational wave community over the last years. Strengthened by our success, we are now ready to take on a new challenge with the Einstein telescope for a third-generation interferometer that can further expand our horizon, our knowledge of the universe, and our technological capabilities. Thank you very much.
Our next speaker is Mirjam Lauwetsink. She is a director of the NWO, which is the Netherlands Organization for Scientific Research, and one of the European funders of the Virgo Observatory in Italy. The NWO also steers the course of Dutch science by managing the country's knowledge infrastructure. Mirjam is a past director of the Mesa Plus Institute for Nanotechnology at the University of Twente. She was also chair of the Dutch National Laboratory for Nanotech Research and Development.
Ladies and gentlemen, it's an honor to be here to witness the IEEE historical milestone for gravitational wave antennas for LIGO, IGO, and Virgo. As director of the Institute's organization of NWO, the Dutch Research Council, I represent the activities on gravitational waves of the Netherlands. This research is carried out by the National NICAF collaboration that includes our National Institute of Particle and Astroparticle Physics, NICAF, and the activities on 6 Dutch universities. And I must say, your research on gravitational waves, with all the developments of the past few years, is truly impressive. It caught the imagination not only of the scientists directly involved in the research, but also of the general public. Your research provided a completely new window in observing our universe and brings deep and significant answers in the exciting journey to the fundamental questions of space and time, our universe, its origin, and its destiny. The challenges of the instrumentation are immense, and like many others, I was particularly astonished when I realized how incredibly tiny these gravitational waves really are. The amplitude was compared to the increase of the level of the IJsselmeer, a big lake according to the Dutch standards of more than 1,000 square kilometers. Its level rises when a single extra drop of water is added. Even then, the gravitational waves we actually measure are smaller by a factor of 10,000. And this is truly mind-boggling. From the Netherlands, we are very proud to be part in this endeavor. NICAF has produced significant instrumentation for Virgo and is, as we speak, involved in various upgrades of the antenna. Students from many universities connected to NICAF are directly exposed to this research and are really looking forward to the next level of more sensitive data in the coming years. Only very recently, NWOI, NICAF, has become a formal member of LIGO, strengthening the international collaboration on gravitational wave research in Europe. Our ambitions are high as we foresee a rich and deep future for this research. Together with INFN, NICAF is coordinating the preparation to construct a next-generation gravitational wave antenna, the Einstein telescope. This ambitious project is still in the conception stage, with one scenario that it will be constructed at the border area between the Netherlands, Belgium, and Germany. The coming years will show how realistic these plans really are and if political support can be secured. In the meantime, the Netherlands, Belgium, and Germany have started to construct the ET Pathfinder, an ingenious and fully operational R&D facility to test and optimize the instrumentation for the Einstein telescope, irrespective of its future location. With first detections of gravitational waves, we entered a new era of exciting multi-messenger science. The prospects of this field are so promising that our universities established new research groups, and the Gravitational Wave Group is now the largest at NICAF. But it also works to strengthen ties with industries and small companies to tackle all challenging barriers for new detectors. This brings me back to the reason we are celebrating the recognition of this research by IEEE. It is an achievement that fully fits this research. I congratulate all members of this wonderful LIGO-Virgo collaboration for this well-deserved reward, and I look forward to the continuation of this fascinating story.
Hello, I am Kate Duncan, the 2021 president of IEEE-USA. In my day job, I am involved in research and development of magnetic nanoparticles. And now I would like to share with you some thoughts on this extraordinary achievement. LIGO and Virgo are excellent examples of results from making long-term commitments in basic research investment. The National Science Foundation has invested more than $1 billion in LIGO over a 40-year period to confirm Einstein's prediction of gravitational waves of over a century ago. Einstein himself did not believe the measurement of gravitational waves was possible because of the technology required to make this measurement was far too advanced for his time. LIGO was a high-risk investment, the largest single effort ever undertaken in the 75-year history of the NSF. The return on that research investment now provides us with a fundamentally new way of looking at our universe. This is truly a monumental physics and engineering accomplishment. The direct measurement of gravitational radiation required an innovative international collaboration applying state-of-the-art multidisciplinary engineering and technology. The confluence of these technologies working together provides LIGO and Virgo with the ability necessary to measure 1/10,000th the width of a proton. That measurement capability enables us to detect some of the most energetic forces that occur in our universe. It is amazing to consider that we can measure gravitational waves produced by the coalescence of two black holes from another galaxy located over 1 billion light years away. The IEEE milestone being dedicated today is in recognition of the extraordinary innovation and collaboration that was required to make Einstein's prediction a reality. I am concerned, however, over the reluctance of making this type of long-term investment in science today. Projects like LIGO and Virgo have always been too big, too risky, and too long-term for private companies to undertake. It falls on the public sector of the international community to support large-scale and long-term projects like LIGO and Virgo. The first LIGO detection simply would not have been possible without the NSF's unwavering support. Policy decision makers must recognize the intrinsic value of long-term basic research investments. We can't build projects like LIGO today using a short-term investment strategy. We must provide the long-term support necessary to make the returns on this type of investment a reality. The potential return on investment in highly speculative research is enormous in terms of what it provides for our future society. This kind of investment is needed to keep our researchers at the forefront of innovation that enables discovery and to disrupt our complacency. As we approach the one-quarter mark of the 21st century, we need to make more of these investments to take on the seemingly impossible problems by applying transformative solutions that allow us to boldly reshape both our knowledge of technology and of the universe. The international array of organizations that made LIGO and Virgo a reality holds a bold vision for scientific research. These scientists and engineers have provided us with an extraordinary example of what we can do when given the time and resources to tackle big projects and big questions. On behalf of the IEEE-USA and the 170,000 IEEE members in the United States, I want to thank each and every person who contributed to the success of LIGO and Virgo. You have shown us and our political leaders what a collaboration of brilliant people from around the world can achieve when they are challenged. I look forward to the future accomplishments of this team and others like it. I would now like to introduce our next speaker, Rich Abbott, who is the LIGO Electronics Group Leader. He has overall responsibility for the electronics hardware at the LIGO site in both Hannaford, Washington and Livingston, Louisiana. Rich came to LIGO from the particle physics world over 25 years ago in the capacity of an electronics design engineer. He is an IEEE senior member, and he played an active role in the organization of today's event. He also was gifted with the task of interviewing the 3 winners of the 2017 Nobel Prize in Physics for today's event. Those 3 gentlemen received that distinguished honor for decisive contributions to the LIGO detector and the observation of gravitational waves. Take it away, Rich.
Firstly, a thank you to Kate Duncan, the 2021 IEEE-USA President, for the kind introduction, and to the IEEE for the honor of the LIGO Milestone Award. I am Rich Abbott, and it is my sincere pleasure to introduce 3 gentlemen who have been a source of inspiration and guidance to so many of us within the field of gravitational research and beyond, the recipients of the 2017 Nobel Prize in Physics for the direct detection of gravitational radiation, Drs. Rainer Weiss, or Ray as we call him, Kip Thorne, and Barry Barish. Gentlemen, thank you for being here today.
Thank you.
Thank you.
I have a few questions for the 3 of you to learn a bit about your personal views on the history leading to the creation of the observatories and to look into the crystal ball to the future of gravitational wave astronomy. So feel free to self-assemble on the answers to these questions. It's watching your interaction that's going to be genuinely fun for us in the audience. So I'll start with the first one. What did you find to be the greatest challenge in LIGO?
People.
I agree with Barry.
We had, well, I mean, it's true, I think, in anything, but we had a very, very large group of very talented people spread around the world that worked on this for a very long time. And that's a complex social environment where different people have different, not just different skills, but different motives and different backgrounds. And I think that's the hardest part. We're pretty good technically. We learn about all that, but we don't get trained as much to do people problems.
Let me answer what Barry said. It's that specific problem that we had was that it was hard for many of us to make the transition from tabletop physics, where you're in charge of all your own world and your own people, to a thing which was much larger than that. And so it had to be organized and into subsystems and had to be organized so it wasn't completely under your control. That was very hard for everybody, but hardest for one of us. It was named Ron Drever. And that was, in fact, I think the biggest challenge we had is, as Barry says, was people. but that was the biggest one. And Kip and I and Drever worried that problem for many years.
I would say there was another huge challenge that was equally large, at least equally large, and that was just how far we were when we began. If you go way back, the earliest epoch in the early 1970s, how very far we were technologically away from having the techniques, the technology, for really pulling this off. And I was highly skeptical initially that it could possibly be done because it was so far away. And it was only after long conversations with Ray in the mid-1970s and Vladimir Brzezinski in Moscow and others that I really became convinced that there was a chance of pulling it off. And while I had huge respect and confidence for my experimental colleagues, nevertheless, it was a long road to hoe. And the fact that you, my experimental colleagues, were able to pull it off is just a tremendous tribute to your skills and your wisdom.
Thank you. So the next question, the news media has written extensively on the black hole and neutron star mergers, but what are some of the indirect scientific insights made feasible by the detection of gravitational radiation? Those things that we in the public might not find obvious.
Well, the thing that I'm the most enthusiastic about is that in the black hole collision that LIGO has seen, we are for the first time ever in human history observing the behavior of gravity and its associated warped or curved space-time, and a situation where the shape of space, the rate of flow of time are changing extremely rapidly. And the processes going on are what we call very nonlinear. This is a whole new domain for observing the warping or curvature of space and time. And it's a regime where we didn't even know the predictions until we had numerical simulations only several years before the observations were made. And the fact that the gravitational waveforms that the LIGO sees agree so beautifully with the computer simulation tells us that the wild behavior of highly warped space-time that general relativity predicts and that we see in the simulation, that it really happening. So it's a completely different regime for studying the nature of gravity of warped space-time, a regime made possible only through the combination of this superb technology and skills and data analysis skills of LIGO and the computer simulations.
I might add there's some surprises observationally already, and that's something we'd always hoped for. So one thing was, of course, to confirm what Einstein had proposed about gravitational waves. But even black holes, the first thing we've observed, we have interesting situation that we've observed ones that are heavier than we thought were likely to be in nature because of the fact that the parent stars are unstable. And maybe we've seen ones also that are too light to satisfy what people thought you had to have, how much mass you had to have a black hole. Those aren't confirmed at this point, but I think as experimentalists, observing things in nature that don't fit the pictures that people have is kind of our dream.
Mm-hmm.
Oh, let me add to that a little bit. I mean, it's an interesting question you ask. What besides gravitational waves? I mean, the thing is, a lot of the thing we're now going to learn, which we don't know anything about, is where these sources, as Barry points out, come from. And I hope that that's going to be one of the more interesting things for what the science of both astrophysics and cosmology. For example, it might very well be that the black holes might come from primordial things. We don't know that. I mean, that's a nice idea. It may not be true, but we don't know right now where these binaries all come from. We can think of other ways. And the other thing is, I hope that, and Kip has said this over the years in many of his wonderful talks about the field, it's a different field than any of the others in astronomy, in the following sense, that you can look inside of things. You see, these gravitational waves don't seem to scatter, nothing, they don't get bothered by anything. So they can go across the whole universe without really changing their character. You can start from one side of the universe that we have, go all the way to the other, and still they come out the same. You can't do that with light. Light gets scattered by everything in the world. And so here is an idea that you might be able to look inside of things that you have never been able to do. And I think one of the things we might find out, for example, is what's went on in the earliest universe. We might find out what really goes on in a supernova. These are things, I guess, in your questions later, but they're directly those things that might very well be new for us.
To my next question, the importance of international collaboration to the next generation of detectors. And traditionally, this has been an effort that the machines that were built in the US have an international aspect to it, but how important do you think that's going to be in the future, these larger machines and the distribution of detectors?
Rich, it's critical. I mean, in fact, we already have much better information about our sources because Virgo is on the air as well, as besides the two LIGO detectors. And I hope CAGRA, when they get sensitive enough, will add to this. We can't point these detectors. That's the important thing. You can't. There's no way to take and aim the detector at a source like you do with a telescope. They're sensitive to pretty much omnidirectional. It's quite a little bit of an exaggeration, but it's almost omnidirectional. So how do we know where these sources are in the sky? We do it by timing. In other words, the first source we ever saw was a binary black hole, which made a signal that came to Louisiana, and then it went through the Earth and came up again up in the Pacific Northwest. That's how we knew that was somewhere in the southern sky. But we had no idea about where the thing is otherwise. So it's very important to use the Earth as a way to get different times. Many detectors, different times. And why is that important? Because you'll learn so much more about what's going on if you can then take that information, where the source is, and tell a real astronomer, a classic astronomer, go look over there. And if they see something, that adds dramatic information to the. It's called multi-messenger astronomy. It's a big new field for the NSF.
So that's from the technical standpoint. I think from the standpoint of doing very risky, challenging science, that all the expertise is not in one place in the world. It's not in the US. And so if you just take LIGO now, our expertise leans very heavily on expertise and contributions that came from Scotland, Australia, Germany, and so forth. And that's only going to be more so. And I mentioned particle accelerators. It's again, there's no way to step back. The expertise is around the world. The people that know the most aren't necessarily in one country, certainly not in the US. And so both in terms of a group of people being able to do a challenging technical and scientific project, and for LIGO, or for gravitational waves, the additional fact that you want to spread the detectors around the world. It's completely a one-way street, I think.
And this international aspect has been the case from the very beginning, going way back to the 1970s, when Ray originally conceived these types of gravitational wave detectors. A group in Germany led by Heinz Billings jumped right in and started developing these detectors there. And the technological developments in there and in Glasgow at MIT and later at Caltech, they fed on each other with extensive interaction between the various groups. And so the foundation on which LIGO was built, as LIGO started to move forward under Barry's leadership, was really an international foundation from the very beginning.
Interesting. Thank you. So next question is a little more pie in the sky, but let me ask you anyway. We've seen the mergers of neutron stars and black holes. What events are you hoping for next?
I want to see a black hole tear a neutron star apart. Let's see that in detail. See the gravitational waves that are coming off from that neutron star as its guts are spilled out into the surrounding universe.
Graphic. Great.
Well, it'd be nice to see a supernova. Now, that was the initial mantra. Turned out that in the early days, we thought that would be the only source. Then they became a very disappointing source because we suddenly realized the neutrinos that Barry was studying would slow down the explosion, would make much less gravitational waves than what the initial thought was. But still, it's a fascinating source. Why? Because what really goes on, you see with gravitational waves, as I said before, you can actually look into what the supernovas do. You can look at the star that actually is exploding. And nothing's going to stop that gravitational wave from coming out of that region inside where the thing is really the dynamics that goes on in the supernova will be exposed for the first time. It's going to be fascinating. I bet we don't get very many of these, you know, and they have to be, unfortunately, most likely in our galaxy. So you got to wait a while. But let's hope we're on the air when it happens.
Oh, yeah.
And I'll pick something else, which just shows this can go in many, many directions. I think next might be, that's really interesting, might be continuous sources. That is a spinning neutron star. And it has the nice feature compared to these other ones that you can keep studying it. We can get, once we find one, we can keep studying it with better observations and so forth, because it's there. It's not just something that happened in a transient way. And we don't know very much about what this compact nuclear system is going to be like. And so the science should be pretty exciting, I think.
That is exciting. Great.
And I think of all the things that we might see, I think the thing that will be most exciting is something we didn't predict, something we had no idea was coming. And
prize gift.
And this is from the very beginning, when we first started thinking about LIGO, this has been my dream and my expectation. And so we will see, but I'm pretty sure it will come. And it could revolutionize our understanding of the universe when that happens.
Excellent.
Kip's been saying that as long as I've known him.
So the last and least technical question and most philosophical, how has this long ride to where we are today changed your lives?
Right.
That's a broad one, I know, but you can pick the top one. I don't know, your choice.
Well, I've gotten older. I like to think a little bit wiser.
Good.
I've come to appreciate my colleagues enormously and appreciate and understand the power of collaboration, the critical roles played by people who have very different skills that they bring to this. But looking in from another point of view, this has provided enormously increased opportunities to inspire young people about science. In LIGO is, and what it is saying is a truly inspirational story, the history of it, and the science that is coming out is inspirational. And I think inspiring young people about science is one of the most important things that we can do as scientists.
Well, I have a much more pedestrian view yet. But I mean, there was one unpleasant part of this whole thing you heard about at the beginning, the problems with making the change in looking at the way you do the work. That was the only one. I think for the rest of my whole life on this thing, it's always been that it's been a lot of fun to work on. Look, the fun comes about by building circuits or by machining things in the shop, or you're going out to the site to commission and it actually works, or you're working on a puzzle and suddenly you find the answer. These are wonderful things to imagine. It's a privilege to be able to do that.
It sure is.
And so the thing is that, you know, and having good colleagues is very important. So just what Kip said and Barry also. So I don't know. I don't want to draw any deep lessons. I think that the one I always say to people is that if it's not fun, don't do it. And you'll never do it. You'll never do anything. You'll just always think of another thing to do better. You know, that's.
Well, it's been a real pleasure speaking with you. That's all the questions I have for today. But I'd like to tell you, on behalf of all of us here today, please accept our gratitude for your work and for being here with us today and sharing your insights. Thank you very much, gentlemen.
Thank you.
Thank you. Thank you.
Real pleasure. Thank you.
Okay.
Composed of two 4-kilometer laser interferometers, housed in immense vacuum envelopes, and separated by 3,000 kilometers, LIGO is engineered to detect tiny vibrations in spacetime, predicted by Einstein, and produced in the most powerful astrophysical events known to human beings. The two NSF-funded LIGO detectors, LIGO Hanford in Washington and LIGO Livingston in Louisiana, were designed as discovery machines, searching for the force carry of gravity predicted by Einstein in 1916, gravitational waves. Virgo operates a 3-kilometer detector in Cascina, Italy, yielding a network of 3 gravitational wave detectors, which operate in observation runs lasting many months. All components of the detectors are fabricated to exacting standards to achieve the required sensitivity, optics, lasers, isolation and suspension systems, control and readout electronics. The integrated observatory relies on exquisite design and componentry. Mirrors must be isolated from ground motion with elaborate suspension systems. The motions of optics are suppressed by a factor of 10 billion times compared to that of the ground on which they're suspended.
At the LIGO Hanford Observatory, we operate one of the world's largest vacuum systems.
The scale is 10 million liters in volume. It has two beam tubes that span 4 kilometers in length, 1.2 meters in diameter, and the operating pressure is a nanotorr, which is comparable to the pressure on the surface of the moon.
After a decade of R&D, the fabrication, assembly, installation, and testing of advanced LIGO components took several years. LIGO's precision measurement required use of cutting-edge electrical, materials, optical, mechanical, vacuum, controls, and IT engineering. Most of the critical parts operate inside the vacuum envelope, and so they must be assembled in clean rooms and be free of contaminating substances and dust. Sensing and actuation instrumentation allows precise and configurable servo control of optics, lasers, and of mechanical motion and alignment.
We have hundreds of control loops in a single chamber just to damp it from ground motion seismically. Has 12 control loops, monitoring ground motion and canceling that out. And then we have control loops to control the optics that hang from that suspension, as well as what we call our length sense and control, or interferometer sense and control, where we then lock cavities. Those have their own control loops.
The instruments can measure length changes between the 4-kilometer arms of around a 10,000th the diameter of a proton. Multi-input, multi-output digital signal processing is carried out in LIGO-designed processor code, overseen by supervisory guardians and configured for low noise and stability by scientists, engineers, and students. LIGO's main laser is in the near-infrared, ideal for low-loss optics and optoelectronics, but some sensing and control acquisition relies on green light, seen here as these systems are aligned and commissioned. Since LIGO was initially conceived, our prospects for success benefited greatly from advances in the engineering state-of-the-art. We are grateful to the IEEE members and our staff and elsewhere whose innovations have enabled these and other precision astrophysical observations.
I wake up every day knowing that I'm going to be working with this group of people that propel me to ask questions every day, that invigorate me to learn something.
At LIGO Livingston, the Science Education Center sees 10,000 visitors per year for a hands-on learning experience about the science and technology of LIGO. Soon, visitors will do the same at Hanford's LIGO Exploration Center under construction. These students represent the future. They are the engineers, the scientists, and the technicians who will form high-tech companies and construct future observatories to improve our world and reveal the hidden in our universe.
We are pleased to have Dr. Sherry Nguyen in our program. She has worked in computer architecture at IBM, is a longtime IEEE officer, has served as United States National Commissioner to UNESCO, and is founder and president of UNESCO's Washington State Senator. Dr. Nguyen has been recognized by the New York Times as a top woman entrepreneur and by Japan Asahi News as a prominent Asian professional woman. We thank Dr. Nguyen for facilitating Washington State Governor Jay Inslee's inclusion in our program.
Good morning. It is my great honor to introduce the Governor of Washington State, Honorable Jay Inslee. After serving in the United States House of Representatives, Inslee has led Washington State as the governor since 2013. His dedication and leadership had brought Washington State ranked as the highest growth in economy, GDP, and STEM workers, as well as the best place for business. Governor Inslee also led Washington State, ranked top 2 in innovation. Most of all, Governor Inslee believed and provided funding for LIGO. Let us all welcome Honorable Governor Jay Inslee.
Thank you, Cherie, for that introduction. I'm really excited to join you and recognize the amazing scientific breakthroughs achieved by the team operating LIGO Virgo, the gravitational wave detection facilities here in Washington State and in Louisiana and Italy. This work has already achieved international recognition, as you know, in 2017, when professors Barish, Thorne, and Weiss shared the Nobel Prize for Physics in their contribution to the groundbreaking discovery of gravitational waves. And today, we honor the entire LIGO Virgo team with a prestigious Institute of Electrical and Electronics Engineers Milestone in Electrical Engineering and Computing Award. Now, for well over 50 years, scientists and engineers have sought to verify Einstein's prediction that space itself is distorted by collisions of massive astrophysical bodies, such as black holes. And the LIGO Virgo team did just that, detecting multiple collisions of black holes and neutron stars, confirming Einstein's prediction, and establishing a new astronomical observatory for future exciting discoveries. I'm especially proud, of course, that Washington State played an important role, hosting one of the 3 laser interferometer gravitational wave observatories at Hanford, and funding it in part. I played some role in that when I served in Congress. About 40 scientists, engineers, and other support personnel call southeastern Washington home as they work to further this critically important research. And I'm thankful also for the work they've done of spreading the education of science in my state and other places. So good luck. Thanks for this incredible achievement. And let's keep searching for truth.
Thank you for providing me the opportunity to represent the great state of Louisiana in this milestone dedication. The accomplishments that we are recognizing today are a testament to the hard work that was made by scientists and engineers from around the world. As you know, Louisiana State University donated the LIGO Livingston site some 30 years ago. Since that investment, the National Scientist Foundation has provided more than $1 billion in funding. We have businesses from around the state that have supported this effort, and as a result, LIGO's impact on our local economy is significant. I would like to thank the IEEE members who are making contributions around Louisiana, and the many others at LSU and beyond who are making an impact, using their scientific, mathematical, and engineering skills. These students will become our future leaders and entrepreneurs leading our next generation. Thank you, and I'm proud of all of you for your efforts in helping Louisiana make strides in the scientific community.
I really thank the scientific collaboration LIGO and Virgo and the European Gravitational Observatory, EGO, that give me the opportunity to join this celebration, and I sincerely congratulate you for such an important acknowledgement as the IEEE milestone dedication to gravitational-wave antennas, Virgo and LIGOs. It's clear that the fact that the scientific and technological infrastructure of Virgo and of the European Gravitational Observatory are included in this path market the most important goals of human progress. It's a fundamental recognition not only of the revolutionary contribution of Virgo's and LIGO's discoveries, but also of the extraordinary and pioneering technologies which made them possible. I know that this technological and innovation could be soon also be applied in many and diverse fields. The study of air quarters, the sea and the climate, smart grids, big data, robotics, and will have in this way also a greater impact of society. Congratulations again, and which for other extraordinary similar success in the future that surely will arrive.
Ladies and gentlemen, good morning, good evening. I am Vincenzo Piuri, former Vice President of the IEEE Technical Activities. I am very glad and honored to introduce you Professor Antonio Luque, Director of the IEEE Region 8, the region in which the Virgo system have been conceived, designed, realized, and installed, where one of the measurement sets of the gravitational waves have been performed.
Hello, everyone. I'm happy to be here at this milestone dedication representing IEEE in Europe, Middle East, and Africa. This milestone honors the technical achievement that led to the experimental confirmation of one of the most important theories in modern physics. But it also highlights the value of international collaboration in research. In this particular case, the distance between the interferometers plays an important role in the physics and the confirmation of the experiments. And the design of the LIGO and Virgo stations had to be considered together initially, also with other detectors in Germany and Japan. That is why this milestone also highlights the birth of multi-messenger astronomy. But there are many other examples where international collaboration is not a requirement of the experiment itself, but a necessity of the way that modern science is done. We are all aware of the most impactful development coming from science and technology in the current environment, which is the availability of several COVID vaccines in less than 1 year, giving us hopes of ending with the current pandemic, thanks again in big part to international research collaboration. According to UNESCO, 1 in 3 scientific articles published in the last years were co-signed by an international collaborator. This is up from 1 in 5 1 decade ago. More impressive is the fact that more than 85% of articles in low-income countries were the result of international collaboration, or 40% in low to mid-income ones. To me, this highlights the importance that developing countries invest into international science for the future. It should also be noted that a big part of this is due to affordable access to scientific publications in these countries, and the role that open science and experiment reproducibility play will only increase. In the same report about international science, UNESCO also mentions that mercantilism characterizes much of national policy making in science, technology, and innovation these days. Everyone wishes to attract foreign research centers and skilled professionals, but few are prepared to discuss frameworks for facilitating this cross-border movement. It is perhaps time that we, as scientists and technologists, push for a return to research that benefits everyone equally, regardless of the original income. I'm proud to represent an organization that strives for that is today recognizing international collaboration in basic research as a milestone and whose aim is advancing technology for the benefit of humanity. Thank you.
I am Giovanni Losurdo, spokesperson of the Virgo collaboration, and I have the pleasure to introduce Professor Nariman, one of the pioneers of gravitational waves research in Europe. Since 1982, with Alain Briet, she gave crucial contributions to technological breakthroughs which have later made observation of gravitational waves possible. Laser stabilization, YAG lasers, injection locking, demonstration of power recycling. Later, for many years, she has been the director of the Artemis Lab and the leader of the Virgo group based at Nice.
So, hi everybody. I will retell the story of the Virgo project along with my colleague Jean-Yves Vinet, and my talk will be on some of the experimental parts. When we started working at the detection of gravitational waves in the early 80s, it looked clear that the proposal by Laureates on the kilometric interferometer could provide a very high sensitive detector. However, our current technology was far from satisfying many requirements. The signal to be detected, those phase variations of light waves, were not well known, but certainly very weak, and we faced 2 problems: how to measure extremely small phase shifts of the light beam, and how to isolate the interferometer from the perturbation of the environment, which come from seismic, thermal, and electromagnetic fluctuations. We worked on solving the first problems, while Adalberto Giazzotto and his team in Pisa were working independently at the seismic isolation. They designed a multi-stage pendulum called super attenuator, which provides excellent results at very low frequencies. In France, we have a small team, 3 physicists and an electronics engineer. We decided to start working towards full-size components rather than focus on the sensitivity of small prototype detectors. We first developed the low-power infrared laser, the so-called neodymium YAG, which were very promising concerning reliability and evolution towards high power. Together with advanced electronics, very fast and low noise to reach record frequency stability and power stability. So within a few years, this choice was validated and adopted by all the other teams. I should mention that part of this work was done in collaboration with Ray's young students, David Shoemaker and Peter Fritschel, who are now prominent members of the LIGO collaboration. Since then, laser power would increase from 100 milliwatts to 100 watts, increasing then the sensitivity of the interferometer by dozens of times and the number of detectable sources by some thousands. In parallel, we developed a program for modeling and computing the requirements of the interferometer to put specifications on the mirror parameters, the alignment, and the geometry of a laser beam. We realized that the requirements concerning the mirror quality were larger than what any manufacturer of optical components could develop. So in the 90s, we decided to build our own mirror research lab, which today stands as a full-fledged mirror facility. This lab in Lyon, which is the basis of fruitful collaborations with advanced European and American optics company and with LIGO, is now the sole facility in the world able to deliver adequate mirrors for all the advanced gravitational wave detectors. I'm grateful to CNRS to support this beautiful experiment since the beginning, and I would like to thank all my early collaborators. Thank you.
Let me now introduce Professor Jean-Yves Vinet. He has given remarkable theoretical contributions to the understanding of how gravitational wave interferometric detectors work and can be optimized, writing relevant papers on optics, thermal noise, scatter light, and developing numerical optical simulation. Moreover, he has been the spokesperson of the Virgo collaboration between 2011 and 2014.
The first detection of a gravitational wave in year 2015 was celebrated as a worldwide event. LIGO and Virgo's 20 years of theoretical and technological developments led to this great achievement, and it was good and necessary. But the first detection had been done by 2 American instruments, even though preliminary technological efforts, the waveform predictions, the data processing, and more generally the physical principles had been widely discussed, and the results shared between the 2 collaborations during a number of years, even if the first official published detection was signed by our 2 collaborations after the agreement confirmed in 2014. This is why I was delighted after the first detection of a binary neutron star coalescence in August 2017 by our 3 interferometers simultaneously, the 2 LIGOs and Virgo, and its electromagnetic counterpart in the NASA and ESA satellites. This was not the first common detection, but the first one, including all the astronomy and astrophysics communities and Virgo. I had then kind of a flashback, and I remembered all the challenges we had to address from the very beginning of this long adventure. I remembered the efforts of my late friend Philippe Tourinck in the 70s to create a gravitational wave community in France. In France, at that time, gravitation was a domain of pure theoretical physics, illustrated by figures like, for instance, André Lichnerovitz and Achille Papapetrou, former professor for me, And I remember the first meeting at Institut Henri Poincaré, which was the temple of general relativity and pure theory in France. This meeting aiming to insert the French scientists, theorists, as well as applied physicists and quantum opticians into this new field for us, experimental gravitation. I remember the long efforts of Alain Briet for obtaining the support of our institutions, the 4 physics institutes of CNRS, skeptic at the beginning, surprisingly. Finally, the Institute for Nuclear and Particle Physics agreed to support our works regarding its resources in manpower, engineers, technicians, and so on, and its culture of large instruments developed at CERN. I remember the friendly collaboration with Italian colleagues led by Adalberto Giasotto after 1985 to finally reach a French-Italian project in 1987. But unfortunately, to my opinion, it was politically impossible to make it evolve towards a full European project. One important point was the choice of a direct full-size approach of interferometry, avoiding loss of time on small-size prototypes problematics. I remember the efforts to develop special technology at Orsay and Pisa for long baseline interferometers, frequency-stabilized solid lasers at Orsay, seismic isolation by the famous super attenuators at Pisa, technology which are now widely spread. I remember the struggle of Alain and Adalberto to get at the end the site of Virgo from a number of land parcels on the ground. After more than 6 years of constructions, we could not have known that after 10 more years of issues and solutions, a clear and complete success would suddenly happen. I then realized that during my lifetime, I would be present for the beginning of multi-messenger astronomy.
Takaaki Kajita is the president of the Science Council of Japan since October 2020. But he is mostly known for his Nobel Prize of Physics of 2015, a Nobel Prize he shared with Arthur MacDonald on neutrino oscillations. As of 2017, he is one of the principal investigators at the Institute for the Physics and Mathematics of the University of Tokyo, and he is also, of course, director of the Institute of Cosmic Ray Research, again, in Tokyo. But understanding part of the cosmic neutrino messenger nature was not sufficient for Takaaki, as I know him. So he also initiated the effort for the Japanese gravitational wave detector at Kamioka called KAGRA. He's currently the principal investigator and will talk to us about KAGRA and also some of his ideas about the future of the gravitational wave field.
Hello, everyone. First, I'd like to congratulate to the LIGO and Virgo colleagues for the IEEE milestone. Our colleagues in LIGO and Virgo have developed extremely sensitive laser interferometers and opened a new kind of astronomy, namely gravitational wave astronomy. Indeed, recalling the history of astronomy, we find that whenever a new method or instrument of observing the universe was developed, discovery of new phenomena soon followed. In many cases, these discoveries revolutionized our view of the universe. Clearly, the discovery of gravitational waves is one of them. For example, the observations of binary black hole mergers have told us unexpectedly that there are black holes heavier than what many star formation theories predicted. The observation of a binary neutron star merger in 2017 was extremely exciting. The follow-up optical observations have even told us that heavy metals such as gold were produced in that merger. Now, gravitational wave astronomy is just starting. More discoveries await us, and the global gravitational wave community is preparing for them. In fact, one very important role of gravitational wave observation is to tell the optical telescopes the location of the gravitational wave events in the sky for the detailed follow-up studies. The accurate pointing of these events is very important. For the most accurate pointing, global collaboration of the gravitational wave detectors is paramount because it is made possible only by comparing the signal arrival time from each detector. If the detectors are separated in the location, the accuracy can be improved. Kagura is located in Japan, far from the LIGO and Virgo interferometers. Because of its location, it can play an important role in the global collaboration of gravitational wave detectors. Finally, we predict that more sensitive interferometers will be constructed in the future, which will advance the gravitational wave astronomy further. In order to achieve higher sensitivity, we have to reduce various noises, including thermal noise. One simple solution is to cool down the mirrors. Kagura uses the cryogenic technology to reduce the thermal noise. We hope that the cryogenic technology developed in Kagura will be an important contribution to the future gravitational wave interferometers. We are all excited with the new gravitational wave astronomy. Once again, congratulations to the LIGO and Virgo colleagues for this amazing achievement. Thank you.
Dr. David Wrightsey is the Executive Director of the LIGO Laboratory at Caltech, where he oversees a 180-person scientific and engineering staff that built and operates the LIGO observatories in Hanford and Livingston. He also holds concurrent positions as a research professor at Caltech and as a professor of physics at the University of Florida. David is distinguished as a fellow of 3 organizations: the American Association for the Advancement of Science, the Optical Society of America, and the American Physical Society. He was the principal investigator for each of the 4 major phases of LIGO funding from the National Science Foundation. Dr. Wrightsey previously served as spokesperson of the LIGO Scientific Collaboration, a group of 1,200 scientists and engineers carrying out the LIGO science program.
Thank you very much, Brian. I have the honor of providing a few closing remarks for the wonderful recognition to LIGO and Virgo by the IEEE. First, I want to express my profound gratitude on behalf of the LIGO Laboratory for IEEE's Milestone Award for the invention of the gravitational wave antenna, which has opened this wondrous new window on the universe. Since 2015, when the first binary black hole merger was discovered, LIGO and Virgo have detected more than 50 gravitational wave events. In fact, we can now detect a gravitational wave event on average about once a week. When our current upgrade program is complete and LIGO and Virgo go back online in 2022, we may be able to push that up to detections of events once every 2 or 3 days. What was once thought impossible by some and challenging by all is now almost routine. But of course, it really isn't routine at all. The LIGO and Virgo interferometers are among the world's most complex and precise scientific measuring devices ever devised and constructed, made possible not only by an understanding of subtle and complex nature of gravity described by Einstein's general theory of relativity, but also by the sustained effort to design, build, test, redesign, rebuild, and then retest the systems and subsystems of these complex interferometers, and then do that again and again and again to achieve the unprecedented sensitivity that we now have. That's engineering, and without it, LIGO and Virgo could not have accomplished what we have. I'd like to note this recognition accorded by the IEEE is also given to the thousands of scientists and engineers who have, over the past many years, dedicated their professional lives to this seemingly quixotic endeavor. I want to quote George Carruthers, a black astrophysicist who designed the first telescope that went to the moon on Apollo 16 and recently passed away. He was asked once by a journalist whether he had any hobbies. He replied, "Hobbies? The projects we have here are so varied that it's hardly necessary to have a hobby." I know that's true for myself, and I suspect it may be true for many of us who've worked on LIGO and Virgo over these past many years. This award is also given in recognition of the important role that fundamental research and its intimate connectivity to society at large. The US's National Science Foundation, France's CNRS, and Italy's INFN made a bold decision in the 1980s and 1990s to fund LIGO and Virgo, in spite of some very real concerns about the possibility for failure. They've managed to sustain that commitment until now, and we hope they continue to do so going forward. The benefits to society are not only about discovering new things about our universe, but also about inspiring curiosity and awe in people who want to learn more about how our universe works. This is very important. Equally important, generations of engineers and scientists take away what they learn from LIGO and Virgo, and they take it into other disciplines to ensure that fundamental research diffuses outward and continues to impact our lives through technological innovation in ways that are hard to quantify, but nonetheless critical to advancing our society. So, once again, I want to thank the IEEE for this marvelous award, and thank everyone who participated in today's ceremony, and also who worked very hard behind the scenes to put the program together. And I want to thank those of you who virtually attended the ceremony. Farewell in 2021.